So I've got a customer that's asking me for better than 1 arc-second, and he'd like to control speed down to 1 millirev per second. So we're going to take a look at a sine-cosine commutating encoder from Quantum Devices. This is a sine-cosine output with 1250 line count, so times 4, 5,000 fundamentals per rev. The commutation tracks 4, 6, or 8. I believe I have an 8-pole motor here. So we can see the sine-cosine encoder option has 1 volt peak-to-peak sine differential, 1 volt peak-to-peak cosine differential, an index pulse, and U, V, and W outputs. We're just going to use U, V, and W and not the inverts, so we just wired the U, V, and W and not the inverts. And of course, it's +5 and ground, and the cable should have a shield, and the shield should be connected to Earth. All shields must be connected to Earth. So this encoder was actually easy for me to install. I am not a mechanical engineer, I'm just an electrical guy. So you can see these little aluminum, or these tabs here that the screws will go into, and the shaft diameter. So I was looking for a motor that had the tapped holes in the back of it to install a standard encoder style. So you can see the mechanical patterns here. And of course, there's a nice cable that we purchased, and this helped to get things up and running quickly, so I don't have to mess with the little tiny connectors. The motor that I'm looking at is Katie Mag motor right here out of Worcester. I picked a very small 48-volt winding that can take a lot of current, and it's got a very low inductance, but we can drive it with the Copley. But the important thing for the mechanical installation is that the back of the motor, besides the shaft with a 0.3750 diameter, there's a bolt hole pattern for mounting the encoder. Another thing I particularly like about the Quantum Devices is there's some very nice documentation of how to install the feedback device. You know, you just press it on gently, you don't smash it on. That's a great picture right there. You can see how the encoder is relaxing into the center, and then you tighten it with a hex screw. Yeah, gosh, this was just so easy to install. There's a timing mark on the encoder, which helps us align things to the electrical cycle. I'll show you a little bit about that. And then you bolt it down. So there's some correct gaps and spacings, and then be cognizant of cable routing. Some of these encoders are very low profile, but very easy for us to use here. So before I show you how to align the encoder and a proper procedure for aligning it, I'm going to do a little back of the envelope math here for the arc-seconds. So Wikipedia talks about arc-seconds here, and we can see the degrees. So if we have 360 degrees per rev, so it's 1 divided by 360. 1 divided by 360. So we have the resolution, and then divide it by 60 for arc minutes, and then divide it by 60 again for arc seconds, and I got 7.7 times 10 to the minus 7. If we look at the encoder fundamental of 1250, multiply that line by 4, we get 5,000 fundamental counts per rev, and then times interpolation of 12-bit only, 4096. All Copley drives can do 12 bits. And we've got this really big 20 million counts per rev. I invert that. Let's put it into some engineering terms here. Okay, so times 10 to the minus 8 is a bunch less than times 10 to the minus 7, so it's like, not only is it less than 1 arc second, it's like 15 counts worth of less than an arc second. With the new AEV drive and the 16-bit A to D, we'll be talking about milliarcseconds next. So here's the quantum devices sine cosine encoder that we have mounted to the back of the motor. You can see there's a really cool glowing red LED on there, so that means the power is connected. This was, again, really easy for mounting. It's a KD mag motor, UV, W, power, so we use the commutating encoder for the 8-pole motor. This is a Copley Accelnet Plus drive that can do the sine cosine with, it's 12 bits, but it has a good E knob, so it's not some crappy A to D that's only really 10 bits. It's got a really good A to D converter in it. Using the Stowe bypass jumper, the USB to RJ11 is real simple and fast. And of course I'm using my XP Power. It's a 48 volt 5 amp power supply. XP Power is a good power supply at a good price. And I just want to show you the new AEV, APV. This is the Accelnet Plus Micro Module. The next time I test this motor, I'll probably mount this drive right to the motor and use the 16-bit A to Ds to get milliarcseconds. Crazy. Okay, so I'm running CME2 version 8.0, and I'm going to run through the setup screen here just to show us, what do we put together here. It's a brushless rotary. I got Halls. I have an analog encoder, and I have a fundamental at 1250, which turns into 5,000 counts per rev fundamental. And I'm just setting the interpolation to 128 to keep the counts into a reasonable number of counts per rev, so I can hit some high speed, so 640,000 counts per rev. And we'll take a look at how to do the sinusoidal commutation and emulated encoder output. That's very cool. So under Tools, Manual Phase, we're going to enable a current vector, and we're going to hold the 0 position here with the current vector. And you can see, I can tweak the shaft a little bit, so that's not very tight yet. I'd like it to hold this Hall state here, UV low, W high. So I'm going to give it a boost of current like 10 times, something more along the rated current. So now the motor's more stiffly locked into a position with respect to the electrical cycles, and then I'll mount the encoder on the back and turn it till I see the correct Hall code. So I'll use the alignment marker first and then tweak it a bit to get to the right Hall code. So you can see in this test setup, this is like a motor manufacturer. They'll pump 3 amps into U, split it down V and W, thereby locking the shaft, and then rotate the Hall to the right code, and then we have a perfectly aligned for commutation feedback device, even with an index marker according to the reference indicator. So after I do the installation in the proper position, I have to figure out the phasing. We'll rotate the current vector and look at the Hall indicators and make sure that it's aligned properly. When you go forward, of course, counts are going up, and the red indicator should lead in both directions with no load. We can change the Hall state and the Hall offset to get the right alignment. If we had a Hall offset adjustment, we would do that after we install the encoder, okay? So you can see, oh, this is a wicked lead and a wicked lag. All right, adjust the Hall offset to 0. I want one file I can save, which is like used with this motor, and then I can replicate it. So this file can be used to manufacture this drive motor, or this motor encoder combination, and make all the motors the same. So that's really important if you're going to be the motor manufacturer. So I'm just going to jog the motor into a good position here. We'll set it to 0. So I'm going to do 1 rev at the motor shaft using the CME scope. You can see I'm going to do 10 revs, excuse me. So I added another 0 here to the 640,000. We'll take a look at how this works out. Now this has all been tuned up. I've got, you know, PP and the current loop tuning, the velocity loop, and the position loop. It's all tuned up. It's pretty good tuning. The notes of interest are, you know, while we're spinning at a constant velocity, what does the following error looks like? If we were running, we'd probably have about plus or minus 50 counts of following error while we're moving. I don't believe this is due to the feedback device. This motor has a little bit of a cog in it. We throw some inertia on it, that'll smooth things out. This cog was in with respect to the electrical cycle, so I already determined that previously. You don't see much quantization on the encoder, so the encoder count has, you know, very good effective number of bits. And you can see we have a move and settle. We do get to 0. So I just saw a plus or minus 1 bit here. So a little more integral and we could settle a little faster, but there's a little bit of plus or minus a count. You got plus or minus a count here of position controls. So that's 12. No, that's not even 12 bits. That's a 128 times interpolation, not a 4096. So we'll take a look at a higher interpolation rate, and I'll have to do the two. Okay, so basically I'm going to change the interpolation from 128 to 4096, which is 32 times more counts per rev. So I got 20,480,000 counts per rev. And if we make a move, a single rev move, we'll see what the trajectory looks like. And this is a crazy number of counts per rev. Speeds will be limited to about 100 RPM based on the maximum, you know, counts per second we can do, but 20 million counts per second. We can still see that there's plus or minus some error while we're moving. Again, that's the torque detent. We have so many counts that we can actually measure it pretty clearly. There's a little integral to steady state. You can see the quantization noise when we're holding position at 12 bits. We do have a good effective number of bits in the drive. So this plus or minus 10 to 20 counts worth of quantization, you know, that could be signal to noise ratio. That could be a little bit of, you know, noise on the system. But you can see, you know, with the Copley quantization here is a couple of bits here. So the next time I'll experiment with the 16-bit A to Ds on the AEV. So we'll try the little guy mounted onto the motor, make a little drive motor package, and see what kind of crazy interpolation we can get out of that. Okay, I think that's it for sine cosine encoders. I hope you like them. I think they're very interesting, and this encoder device here from Quantum Devices in high quantity is very reasonable. I think I picked mine up for like $200 from the local distributor. But if you're gonna consume a lot of them, then you probably get a really good deal. Hey, thanks for watching.